Hello, welcome. Thanks for joining us this afternoon. My name is Scott Lindberg. Let's see if this works. There you go. A little bit about me. I've been in the industry, you can tell by the gray hair, for just a little bit, since 1983. Started out as a sales rep in Colorado, changed careers, sold semiconductors for a few years, got out of that, and 10 years ago, I joined Quell Corporation out of Albuquerque, New Mexico. We'll talk a little bit about that, but first, I have to share my family. I'm a father of four. I got 3 daughters and 1 son. This is my grandson. I'm really sharing this because the new addition to the family is now 4 weeks old. And this is little Adeline Cherie, my daughter. I gifted me with her 4 beautiful weeks ago. And pride and joy there. Powell Electronics right over here. Robert, say hi to Robert. Robert is with Powell Electronics. He brought me over here to share some things with you today. They are a distributor for us worldwide, and very excited to be here. Thank you, Robert. Andy Brayford is our European distribution and sales manager. He's joined us today as well. Quick question, who's been to a pub? So I love pubs over here. We don't have pubs necessarily in the US. What's the name of your favorite pub? You don't have a favorite? Anybody have a favorite pub? What is it? The Golden Rail. All right. Favorite pub? The White Horse. The White Horse. Well, last night I went to a pub. Have you ever been to a pub called the Red Lion? Everybody's been to a pub called the Red Lion, because I learned that the Red Lion, there are 516 pubs in the UK called the Red Lion. There's 460. So if somebody says, hey, let's go to the Red Lion tonight, where are you going to go? There's so many. 467 Crowns. Royal Oak, 393. Last night we were at the Royal Crown, the Old Crown, close by. Love it. I'm going to start a pub in the U.S. called the Red Lion, I think. So, all right, Quell Corporation. We're in Albuquerque, New Mexico. We've got about 50 people, 45, 50 people today. We have 12,000 square feet. Everything we do is made in the United States. We're ISO 9000 and AS 9100. We're not a new company. You may never have heard of us before, but we've been around since 1994. We patented our first product in 1995. We've done lots of different things. Today, we've supplied over 2.5 million EESeals in high-rel applications. 2019, we were acquired by a company called HEICO. HEICO is about a $2.5 billion company, surrounded by aerospace and military and defense. Our products, we're going to talk about this in more depth later, is called an EESeal. It's a silicone rubber insert that goes into a standard connector and makes a standard connector a filtered connector in a matter of seconds. We also can do stuff on the rear. We'll talk a little bit about that as well. On the back side of a connector, if you need a pi filter or you need higher voltages and things like that. So today we're going to talk a little bit about the design process when it comes to EMC, testing, some different options, specsmanship stuff that we see when we're doing things, and let's just jump in. All right, what do we do? What do we do? And when I say we, it's us, right? Engineers, everybody an engineer, pretty much, yeah? All right, what we do is we protect the world. And I was thinking about this because there's a war in Ukraine, there's a war in Israel right now. What we do is important to the world. It's important to intelligence. It's important to our military and defense. It's keeping people safe. That's what you do. We get to help you do that, but it is so important what we do. When we send a missile someplace, we want it to hit the target, right? When we're in an aircraft, we want it to land safely, right? And without the EMC capabilities that you guys do, that doesn't happen. So we protect the world, and I appreciate what you do and how we get to help you with that. All right. EMC, EMI, RFI, what happens? Every piece of electronics is a source of noise, electronic noise. Every piece of electronics is a victim of electronic noise, either radiated or conducted, right? And you do the tests for MIL 461, DO 160, whatever it is, to protect against that noise, a susceptibility, conducted, radiated, right? That's what we do in our design. The design process. When we start our design process, we go through a lot of different things. When we do our design, the worst part about my job is you do not want to use my product. right? You want to do the design. You put your TVSs, MOVs, capacitors, and everything on the board. You protect your box with power line filters, power entry filters. You do shielding. You do everything you can up front in the design, right? And if with any luck, you go to test. And when you go to test, the system passes, you go to production, and you're done. Life is good. Works that way every single time, right? Well, maybe not. Sometimes you go to test and you failed it. You went to the chamber and you failed your test. You're out from 50 to 200 megahertz. You got a big spike at 150 and you need to solve the problem. You have a couple options. You can go back to design, or by our desire is to get to production and get out of the test lab and get to production. If we go back to design, we're going to have to do something different. We're going to spin the board, right? Spinning the board is very costly and it takes time. So if you spin the board, how long does it take to get a new board, get the new process? It may take 6 months, right? And it may take $250,000 of effort to do that. Then you go back to test and you have to retest. And that testing is costly. And then you're still hoping that you've solved the problem when you get back to test. And if you didn't, you got to respin the board and do it all again. You also have the scrap, that you have to scrap everything you've done previously, right? So there's a lot of cost by going back to design. So if we could change it and we're in the lab and we can solve the problem, which could be ferrite beads, it could be shielding the cable. It's not wrapping aluminum foil around the connector to make sure nothing happens, right? It's not that. That's not production worthy. But if we can figure out some way to be in production right out of the lab as quickly as possible and in production, we'll save the company time and money, right? And then we get this green line. If we can get that green line, we're in great shape. We're in great shape. So a lot of different ways to do this. Connectors is really where we're at. So in the connector standpoint, we've got C filters all the way down to pi filters and T filters, right? Various solutions. The goal is to get us out of the lab and into production. I always look at this as a hammer. A tack hammer, if you're going to put a tack in the wall to hang a picture, you can use a tack hammer. You could also use a sledgehammer. They both accomplish the same thing. You can use, if a C filter solves your problem, why use a pi filter? If you need a pi filter, you need a pi filter. If you're breaking up concrete, you need a pi filter, right? But if you're putting a tack in the wall, you can use a C filter. When you look at what's inside of these devices, if you can use a chip, they're less expensive. If you have to use a discoidal capacitor and a pi filter, they're much more expensive. If you use tubular capacitors, they're more expensive. So we want to think about that cost, right? Price, delivery, quality, service, technology that goes into these different products. When you look at them, a C filter will give you an insertion loss here. You can see the blue line. Pi filters will be at the orange line. It is in theory, better filter. And I say in theory because I see lots of them, and they're not always better. They're not always better. So the best option, what's the best option in all those? It's the one that solves the problem. It's the one that solves the problem. They may all solve the problem. We want that green line so we can get into production. All right. Now, this is an example of a customer that came to us and he said, I would like a filter. And when you look at the noise floor, right, this is ambient noise right here in the lab. He tested. The black line is his original baseline test. He sees he's out all over the place. He calls us, he gets an EMI filter from us, he drops it into his connector. He gets the red line, he's down at the ambient floor and he goes, that doesn't make sense. It's too good to be true. And so he extracts our part from the connector and and I love this, he says confirming his baseline because he didn't believe it. And he's out and he drops it back in with the blue line and he solves the problem. Right? And if you did this from the hammer standpoint, right, the tack hammer, this is a C filter. It got us to the noise floor. He could have used a pi filter, and where would it have gone? To the noise floor, right, to that same spot. So which is the better solution? It's the one that gets you out of test. He sent an email and said, wow, I had to try it twice. And I have a lot of customers that try our parts twice because it's too good to be true. It's too easy. It's too simple. All right, specsmanship. We get a lot of people that use pi filters or different filters. And the other day we had somebody come up with a spec. This is the spec that they use. And they're using an LC filter. They've got a feed through, and I'll show you that part. But this is a 5,000 picofarad, 5 nanofarad device, plus 100%, minus 0% tolerance, right? It's a 5 amp device. They're getting 70 dB of attenuation at a gigahertz. That's the spec that we have to meet. They want us to meet it. The reason they want us to meet it is they have 52-week lead time. It's very expensive. This is the feed-through plate. This ferrite is cracking constantly, so they have quality issues. They want us to meet that spec. So we look at that spec. They send us the part. We test that part. The spec is this dotted line. This is the way that part worked. This part solved their problem. It solved their problem. They went through test. They tested it. They solved their problem, put their hands up and said, go to production, right? Then they found out they had a quality problem with the ferrite, and they didn't look at the spec. It didn't matter what the spec said. What mattered is it solved the problem, right? They're in production. Now they have an issue. So they came to us. We don't do feed-through plates, right? But we're trying to figure out what we can do to help. So what we did is we took a standard D-sub connector, not a feed-through plate, and we put a C filter in there. We tested our C filter against the LC filter. We do not meet that spec. We're never going to meet that spec. They don't meet that spec. But if you look at our part, the green line, it's a better filter. It filters more out, right? And then we come and match their specs pretty closely. Does that make sense? Say yes. Yeah. Now, can they drop our part in as a replacement? I don't know. They have to test it because they could have some high-speed data that's not getting filtered out here, but we filter it out here. So I don't know if they can use us or not. So we've sent them a sample, say test it. It's in a D-sub. We'd put it in a 15, they need 10 pins, we'd put it in a 15-pin D-sub, only filter the 10 pins. It's a different form factor. But the key here is people don't necessarily meet the spec, they say, but it doesn't matter if it solves your problem, right? I want to meet the spec. Here's another one company that we don't do a lot of second sourcing, because if you need a second source, I've got to match it perfectly, right, to drop it in. And it's very difficult to match perfectly. So here's two pi filters, right? It's a pi filter from a competitor of ours and our own pi filter. In this case, you can see our part performs better than theirs, but it's not a drop-in identical part. Will it solve their problem? Will it work? It could, but the proof is in the testing. The proof is in the testing. So that's why you use a C filter versus pi filter. If you approve a pi filter, you're stuck. If you approve a C filter, frankly, you're probably stuck as well, okay? Because you're not going to test them all. All right, solving the problem. Here's another application. It's always important. So when you're talking to customers and you say, hey, what do you need? And then I say, well, how many are you going to buy? That quantity thing is always an awkward thing. But it's very important to tell the sales folks or the engineers that you're dealing with how many you're going to buy. If you're going to buy 1 million parts from me, I'm the wrong guy. I can tell you that right away. If you're going to buy 10 parts from me, I'm the right guy. This application is going into a military vehicle. They're going to buy 50 pieces. That's all they're going to buy, 50 pieces. They are in the test lab. They're in the chamber. They're in the test lab. They're out from 2 megahertz up to 1 gigahertz. That's their baseline test. We came to them and we designed a part. We were trying to be cost effective. This was right when I got to Quell 10 years ago. We were trying to be cost effective. We ended up putting 3 capacitors in parallel on each of the 4 pins. Seemed like a great solution, 150 nanofarads. Here's their scans afterwards. Didn't do a thing. They're going to buy 50 pieces. They're in the chamber. They called us up. So we designed, built it, and shipped it to them in 24 hours. They tested it. It didn't work. We redesigned it. So now we get it out of this baseline. We looked at it. We said, all right, we got to throw the kitchen sink at this. So we changed our design. We added multiple capacitors. And it's not just these 5 capacitors. It's multiple capacitors of those 5. We changed the design from the 3 in parallel, and we went to 12 devices in parallel on each of the 4 pins. A much more expensive filter than this first one. Trying to be cost effective, throwing the kitchen sink at it. A lot more ground wires, right? A lot of stuff in that. Now they come back, we've solved their problem. They have a few little variances that they got waivers for, but we solved their problem. We got them out of the lab. They bought their 50 pieces. We did them a disservice with the first design. When you say 50 pieces and you're in the lab, if our part is $1,000 a piece, and it's not, but if it was $1,000 a piece, And they're going to buy 50. That's $50,000. How much did the extra 3 days cost them in the lab? They have a Humvee in the lab with all the associated engineers and all the equipment in the lab cost. I bet that cost them $500,000 for 3 days. Crazy amounts of money to be in the lab. We got to get you out of the lab. Again, now if you're going to buy 1,000 pieces, I got to be cost effective. Different animal. All right, the Quell solution. When you look at Quell, we make a silicone rubber packaging technology where inside the silicone rubber, we embed chip devices, typically 0402, 0603, sometimes larger, sometimes smaller. We use all the properties of the silicone rubber to our advantage. You can twist, turn, stretch, compress our device, and not damage the circuit inside. It's a totally custom circuit. You put it over the pins of the connector, get the pins to protrude through the holes, use the mating connector to seat the device at the bottom of the connector and create a filter connector in a matter of seconds. There's no tooling, just the mating connector in your fingers. There's no soldering involved. You can do it for EMI, RFI, transient protection. You can do a pull-up resistor. You can do shorts, grounds, anything you can think of. We even did one with a thermistor inside to measure the temperature inside of the connector for a customer. We had one customer want to put resistors in there to heat up the connector in space because the connector wasn't rated for the low temperatures. We did not do that one for whatever reason, right? The design of this, we use conductive silicone as our contact mechanism around each of the pins, each of the treated pins. We use highly conductive conductive silicone around the edge to make our connection to ground. We use 3 mil anneal copper gold-plated wires to make a contact from the conductive silicone to the capacitor and then to ground, or we can go pin to pin. So we go pin to pin, pin to ground. We can do special circuits. We can do series and parallel as long as there's room inside, right? It just depends on what you need. Every pin can be treated uniquely. We then put it over the pins. We sandwich it in between the connector. We add about 20 to 32 mils inside the connector. The key is we want to maintain the pin to socket of the connection, right? And it's been tested for that, right? What else? Oh, I'm going to go back. Here, it's a three-dimensional product, which is really cool. We don't violate the interfacial seal inside a 38999 connector, right? And it's three-dimensional in that it will adjust inside. So it'll take on that cork and bottle aspect inside the connector, right? So you maintain the interfacial seal inside. Some pictures. I like to show this one because of the discrete devices. You can see the discrete capacitors there. Every pin can be treated uniquely. So we always ask you, what are your voltages on the pins? What are your data rates on the pins? If you have 120 volts on a pin and I give you a 50 volt capacitor, you don't have that capacitor very long, right? If you have Ethernet and I put a 47 nanofarad cap on there, I squash all the noise and I take away your Ethernet. Right? I have people that come and say, put 47 nanofarads on all the pins, and we do it. And we send it to them and they say, it works great, but my video signal's gone. Well, you didn't tell me you had video signals, right? I need to know the whole story so I can do it right the first time. So you go into the lab, you find out you've got an issue. You got spikes from 50 to 200 megahertz. You need to mitigate that problem. It's very simple from our standpoint. We just go to the appropriate attenuation chart. I'm going to come in here and I'm going to pick this 1 nanofarad part. Right, that probably because I got a 15 dB spike at 150 megahertz. And so I'm going to pick that, I'm going to put it in. And if everything goes according to plan, I'm going to get that green line. If I don't get that green line the first time, I'm going to get you another part right away. Sometimes you get that waterbed effect. I squashed it all, and over here at 300 megahertz pops something else. Gosh darn it. So we'll get you another one, and we'll try it again. Just like we did on that military vehicle, we did a different iteration of it to make sure it works. In some cases, we can't do it with a single capacitor. So I mentioned we can do series or parallel construction. So in this example, you can see there's an extra spike out here. We want to use a second device. So I use this example. This is for a tank. This is for a tank. And here we have 6 1206 devices in parallel and in series to protect these power pins, each of these power pins. We also have 4 47 nanofarad caps on those 4 with squares. And I've got 2 that are open, right? Because they don't need to be treated. So as long as I got room in here, I could put another 30 capacitors in here. I got plenty of room. So we can do lots of things with that. So let's have some fun. In your bags, you have what we call a try me sample. Pull that out. We're going to make a filter. We're going to make a filter connector. This is how easy, and you can do this at home. You just need a filter connector. So we sample, we give away D subs in these Try Me samples because 38999s are expensive. Be nice to be able to give out 38999s. I'd love to do that. So if you take the EESeal, you can see it here. You've got it, and just before you do that, you can feel the edges. If you feel the edge of the connector, you can feel that there's a little raised edge. That's the conductive silicone, right? There, if you look in, there's a card. And on it, there's a green D sub. It's a 15-pin D sub. It has 5 capacitors in it. Sadly, they're probably symmetrical, so you could put this in upside down, it would still work. But in some cases, you know, you'd filter pins 1 through 3, and the rest of them would be open. If you flipped it upside down, it wouldn't treat the right pins. We're going to take the EESeal logo face up. Face up. Okay? We're going to put that EESeal over the pins. Just put it over. I'm going to show you a couple things. When you put that over there, notice it's a little oversized. It is the shape of a D. The EESeal logo is up. It's a little oversized. It's a little oversized on purpose because we want to use the compressive forces of the silicone rubber to make sure we get good grounding to the receptacle. In addition, the pinholes are 10 to 50% smaller than the pins of the connector, because we want the pin to go through the EESeal, stretch the silicone rubber, and then it compresses down. All right, once you've got it over the pinholes, over the D sub, you're going to press it down. You're going to press it down until you get the pins to protrude through the holes. Now, here's a little warning here. Once you do this, and it's at the bottom of the connector, you can't get it out. All right? You can't get it out. So we're going to partially insert it until you get the pins all protruding through the holes. Right? So you get them all protruding through the holes. And it should look like that. Everybody there, say yes. All right, now one of the questions I love is, what's the best mating tool? Well, the best mating tool for all of our connectors is the mate for the connector. So if it's a 38999, you use the mate. And all you're going to do, once you have it all protruding through the holes, you're going to mate that connector. And you've now made a filtered connector in about 60 seconds. If I hadn't talked so much, it could have been about 15 seconds, right? Everybody successful? Jerry, did you do it? You were not successful, were you? You got big fingers, I guess. So once it's seated at the bottom, it's there. It's not going anywhere. And so one of the questions we talk about is durability. So mates and demates, 500 mates and demates on a 38999. It sits at the bottom. You don't pull it out. You can extract these if you need to do some testing on it. All right. Nice job. Another product that we just announced last year is called EESeal Plus. We've actually been selling it for several years. EESeal Plus, same concept. We're using discrete devices inside of silicone rubber. This design here, we use conductive silicone as our entire contact mechanism. So you basically have an entire ground plane, right? You have an entire ground plane. This lowers the inductance, lowers the contact resistance, improves the attenuation. We use discrete devices, but we can also use an integral device. Capacitors are made with a series of conductors and a dielectric, right? MLCCs. All we're going to do is we're going to take conductive silicone and put a dielectric here. So the construction here, this is the what it looks like, little cutaway. The brown is the highly conductive silicone. And we take conductive silicone around the pin, and then we break it with non-conductive, basically making a flexible printed circuit board, right? And then we put a capacitor in there. So we break that. So we go from pin to conductive silicone through the capacitor to the ground plane. Simple design. Now, if we're going to do an integral capacitor, making our own capacitor, essentially zero inductance, we get rid of this capacitor, and now we just put a dielectric there. The space inside the capacitor is limited, so we can only make a small capacitor. So if we look at this, let me go back. It'd be about 4 to 6 picofarads inside. Comparing EESeal versus EESeal Plus. And this is also something, if somebody comes to us and say, I've got a 47 nanofarad filter, can you do that? Yes, I can. Is it going to operate the same as the Cinch 47 nanofarad, the Amphenol 47 nanofarad? I don't know. Probably not, because our inductances are different. I've got 2 parts that I have, an EESeal and EESeal Plus. The blue line is EESeal. To mitigate 80 megahertz, an 80 megahertz peak, I've got to use a 2.2 nanofarad, 2200 picofarad capacitor. In the EESeal Plus, it's got different inductances. So I have to use 6.8 nanofarad. It's a totally different. So if I put in, somebody said, can you put 2.2 nanofarad in there? Yes, I can. Is it going to operate the same? Test it. You have to test it. I can try to make it the same, but you can see the difference. In this example, we actually had outages from 50 to 200 megahertz, right? We tried it with the EESeal. We needed to use 3 capacitors in the EESeal because the peaks were too high, right? With EESeal Plus, we were able to do 1 capacitor. Again, this is 1,000 pieces a year, so we're trying to be cost effective. More cost effective to use 1 cap as opposed to 3 caps. If you compare them using the same capacitor, right? So now in this example, the green line is the EESeal with a 4 picofarad device. It's basically hitting about 2 gigahertz. The blue line is the EESeal Plus with a discrete 4 picofarad device. Now it's hitting about 3 gigahertz. The red line is the EESeal Plus with the integral capacitor, basically 0 inductance. And now we're mitigating noise in the 20 to 100 gigahertz range, right? Much more effective at higher frequency. So when you tell us, hey, I've got a problem at 100 megahertz, we're going to pick the right solution for you. You tell us I got a problem at 20 gigahertz, I know where I'm going. I know where I'm going to go. Here's an example in a Mighty Mouse connector. It's not the best connector for that high frequency, but this is a customer who came back to us and said, here's our baseline, and they got 21 dB at 16 gigahertz, right, using the integral capacitor. I said it, we haven't talked about this. We just announced it really a year ago, the EESeal Plus, but I've been selling it since 2014 to some military applications where they were getting 20 dB of attenuation from 20 to 40 gigahertz. And we're still selling that today. Sometimes you don't have control over the pins of the connector and you're stuck with a socket. Sometimes you'd have high-pot testing, and this one here is an example of where they had to do high-pot testing. They tested it on the front, it solved their EMI problem. Then they went and did high-pot testing, and they said, oops, it blew up. Why did it blow up? What'd you do to it? We did high-pot testing. You didn't tell us you're gonna do high-pot testing. The capacitors that were in there will not survive. So we put it on the rear. We needed to use 0805 caps, and they were higher voltage. Now we passed the EMI, and we passed the high-pot testing as well. So we need to know the whole name of the game. But we can put it on the rear of the connector if you need to as well. And because we're on the rear, we can now do pi filters as well. 90% of our business, military defense, aerospace, space. We do some medical, we do some industrial, some telecom, some transportation, but 90% of our business is military defense, aerospace, and space. It has to be rugged. We've done the environmental testing on all these products because it has to go through this. Shock, vibration, salt spray, all this stuff. Durability, I mentioned 500 mates and D-mates, right? It has to be rugged, it has to be reliable. Everything we do is custom. Everything we do is custom. So, because your application is different, right? So I've got some samples over here in the Powell booth. I've got a 151954. I think I have a slide on it. Maybe I do or not. I don't remember. It goes into the 787. It has 15 MOVs in parallel protecting one pin for 250 amps of current during a lightning strike, right? It's a 15 shell size. It's a 19 pin out. It's totally different than what you need in your 1519. Nobody's going to need that. I've got another 1519 that's totally different. It's custom. It matches your application specifically. Pin to shell, doesn't matter. There's no tooling cost for what we do. We do charge an NRE when you buy a part, and the NRE is an exorbitant $350 to $1,000. Very lightweight, weighs less than a gram, and doesn't take any space because it's inside the connector, right? So it's a space-saving device. You can retrofit. On the 787, they retrofitted about 2,000 of our devices into the fleet of 787s when they first designed this in. We think we're pretty fast. So you're in the lab, you test, and you go, oh crap, I got a problem. What am I gonna do? You call us. You give us the information we need. We can design, because we're over here in the UK, we can design, build, and ship it today. A totally custom product. We'll ship it today and you'll have it however long FedEx and customs takes to get it to you, right? So we'll ship in 24 to 48 hours. Our lead time, our standard lead time is 6 to 8 weeks, but the real key here is or better. You need it when you need it. We've got a call in the last 24 hours. Somebody in Israel needs some parts for a radar system and they need them now. And we're shipping them in 5 days. We're shipping them in 5 days. That's what they need. We do charge an expedite fee for some of this, but we'll get it to you when you need it. From a price standpoint, typically we'll save you 20 to 50% just general cost over a filtered connector solution. If you buy a filtered connectors today take 13, 26, 52, and the other day I heard 94 weeks to get a filtered connector solution. And again, we're faster, but we're going to save you just cost straight up. We're also going to save you cost in terms of time to market, scrap, redesign, all the things we talked about earlier. And it's pretty easy to assemble. Who's who in the zoo for who we sell to? It's pretty much everybody, anybody that you can think of. If they're not up here, I probably just don't have their logo. I think we're pretty much in every space flight, at least out of the US these days. I think we're in every land vehicle. I can't prove that, but I know we're in a bunch. I know we're in the Humvee, the Bradley, we're in the M1 Abrams, we're in the, just keep going on and on. And when it comes to fixed wing, commercial or military, we're in most of these aircraft, the F-35, the F-18, the A-10, 737 MAX, 787. We were on the 747, all those kind of things. But we're in all these customers, but it has to be high value electronics. It's space, it's military defense, it's aerospace. High-end medical, we sold a lot during COVID because we had a lot of stuff in blood analyzers, so we do that as well. When you come to us, we have really 6 questions. We need to know what the connector part number is so we know what to fit it into. Sometimes we'll ask you to send us a connector. If I've never seen it, I've got one right now that we're actually having a connector sent to us. We see all the dimensions online. We've made a part for it. It didn't do what we expected it to do. We say send a connector because it was doing something unique. So we're going to resize it once we get that part to fit check. Then we need to know what your problems are. Could be the scan. I'm out from 50 to 200, or it could be just give me the description, right? I like to see the scans because I know exactly what I got to hit. What are the voltages on the pins? So I size the cap right. What are the data rates? Do you have any transient issues? And where do we ship it, right? If we get that, we're in great shape. I'm going to skip a couple things here. I'm going to show you this slide. This is the one I was talking about for the 787. This is that 1519. And in this case, the average aircraft, my research says that an average aircraft gets hit by lightning once or twice a year when it's in the air. And the application here is the box manufacturer was that when the aircraft got hit, it was damaging their boxes and they were grounding the 787 after that lightning strike. Boeing, of course, is not happy when their aircraft is grounded, right? And neither are we when we're trying to fly them. So they came to us and they wanted to mitigate the 250 amps with the current. And so we put 15 MOVs. We did 4 iterations to get through this test. We gave them 4 different iterations trying to pass this test. These MOVs are all matched MOVs, and they can take hundreds of strikes based on the testing that they did. They went and environmentally qualified it in their box, right? And then showed it to Boeing, and then they retrofitted the fleet. And today there's 75 to 100 of these on every 787. Now, when we talk about lightning is tough. We do not survive direct lightning hits. We're only as good as the components we can put inside of them. So when you have a transient or lightning issue, we want to know what it is. What's the waveform you're going to have to deal with, right? Certain things. So waveform 3, level 1, we can put a 470 picofarad device. That's as big as we can go, right? So depending on what your transient is, lightning or ESD, we're going to put the right component inside of there. The time, right? That waveform is really, really critical for us to design the right part for you. And size does matter, right? We got to have room. If you've got a big connector and we can put lots of things in there, big devices, we're going to have better luck, better success, right? If you have, like in that 151954, that one for the 787, I'm only protecting one pin. So I can put 15 devices protecting that one pin. If there's room, I'm in much better shape. Let's see, what else might be fun and exciting? We have, when it comes to connectors, I really don't care what connector you go into. Typically, we go into 38999s, 26482s, 5015s. I do D subs, I do air inks. The smallest connector we do is micro Ds. We don't do nano Ds. There's just not enough room for the capacitor inside of it yet, at least not for us, right? So we don't care. We don't care who the manufacturer is. We just want you to go to Powell. Since they sell a bunch of connectors, you can buy them from Powell. We also have a new product, and full disclosure, we haven't sold one of these yet, but I'm excited about it. It's called EESeal, and it is a highly resistive device. There's no components in here. We think it's going to be very good for space. We also think the Navy might be interested in it. A lot of ESD on aircraft carriers. But for space, if you've got a floating pin in space, this is basically like an ESD floor mat for your connector. And it's an ESD bleed device. So it's 10 to the 7th, 10 to the 10th ohms, right? And it just bleeds off that device. We also see it as a potential for cable discharge. So when you're assembling a box and you take a cable and you drag it across, you can create that ESD inside the cable, right? So you have to discharge that manually. You would just made it together and it'll discharge it. It'll bleed that off. We also are doing some stuff. You guys are the ones that come up with the best ideas of stuff that we can do. Right? And so I met a customer and I said, here's what we do. We put, circuits inside of silicone rubber. And they said, well, can you just do a gasket? I said, we don't do gaskets. We do custom circuits that you can put in your connector. He says, you put holes in silicone rubber, don't you? I go, yes, I do. So I made a gasket. So for him, we made a non-conductive gasket, but now we do conductive gaskets as well. So here we're just grounding 2 pins inside of an air ring. Here's a short to 1 pin. So anything you can think of, we can try to do. The website has lots of information on everything we've talked about today and more. There's all sorts of white papers for design. There's blogs. There's informational content that you can go and grab and look at. There's also some videos. I love this video. Jay Skolnick is a consultant. He's a consultant in Albuquerque. He came into our facility and said, give me a tour. I teach people EMI and I teach people ESD. Took a tour, he went away. 6 months later, he calls back and says, hey, I need a sample of this part for a 5015. Great, we sent it to him. He comes in 3 months later and he says, look what I did. And he shows us this box that demonstrates it. We've got a video over here at the Powell booth that'll actually show it to you. So he demonstrates to his entire class now with a video as opposed to the hands-on demonstration, right? But it's a great video. You can watch that at your leisure. All right, any questions, comments, or thoughts? All right, I got this the other day. Uncle Jay, do you know why hummingbirds hum? Anybody know? Yeah, no? Bad filter capacitors. That's why, yeah. That's why they hum. Yeah? See, yeah. You're going to tell that when you get home. Uncle Jay probably doesn't understand it. Hey, we're at the stand next door at Powell. Robert's right there. Wave to Robert. Come see us. Love to show you. What a whole slew of samples to show you. I appreciate your time and attention. Thanks very much. Let's get you a sample in 24 to 48 hours, and I appreciate it. Thank you very much. Have a great day.